Hey, Frosty. Here's a little treat for you. Can you sit? Can you sit? Good boy, Frosty. Okay, hold on. Sit. Sit. Good boy. Okay, can you sit? Sit. Come on. Frosty, sit. Sit. Shake. Shake. Okay, good boy. Okay, Frosty. Here's some more. You go eat those bones. Okay. Um, Today I want to talk about spiral growth and Fibonacci numbers. Is there a connection between spiral growth and Fibonacci numbers? And first, to do this, I wanted to talk about the term gnomon. In Greece, in Rome, a gnomon was part of a sundial. It was the part that the sun would cast the shadow on. It was perpendicular from the base of the sundial. And the whole thing about the gnomon is that it was standing up perpendicular. And a gnomon also could, instead of being a triangle, it could just be like an L shape, like this, as long as you have something standing up straight. And gnomon came to mean, okay, something that you add to a shape in order to make a larger form of the same shape. So where that came from was in the study of square numbers. If you study the square number 4, you can see that you can take 4 dots and put them into the shape of a square. And then if you look at the next largest square number, 9, you can form that by taking 9 dots in the shape of a square, and you can do the same thing with 14. And one thing that the Greeks noticed was that to get each square, you could do it by adding the next largest odd number in the shape of an L to the previous square. So if you take 4 and you add the number 5, you get 9. And then if you take 9 and you add the number 7, 1, 2, 3, 4, 5, 6, 7, you get the number 16. The sum of the first odd numbers always gives you a square number. Now, in this case, the number that you add to get the next highest square was in the shape of an L. That looked a lot like a gnomon. So they said, okay, the shape that you add to give the next largest shape is going to be called a gnomon. And that's just where the name comes from. Now, the gnomon, one thing that we've talked about is golden rectangle. And the golden rectangle has a very special gnomon. And it is related to spiral growth. So if we take a golden rectangle, and this is the symbol phi that we're using for the golden ratio. The Greeks didn't use this for that at all. They called it something else. But nowadays we call it phi, 1.618. And if you add to this golden rectangle a square, which is on the long side, it turns out you get a golden rectangle that's facing the other way. The first golden rectangle is facing up. Now this golden rectangle is facing that way. And so the gnomon of a golden rectangle happens to be a square. So that makes it a very special rectangle because it has a square gnomon. It's the only rectangle that has a square gnomon. Now, you can see that that's true just by looking at the ratio of the long side to the short side of the golden rectangle you started with, and then comparing that to the ratio of the long side to the short side of the larger rectangle. And if you do that, you get this equation. Well, this is the equation that we know is satisfied by phi, the golden ratio. Because if you cross multiply, you get phi squared equals phi plus 1. And that's just the equation that phi satisfies. So the golden rectangle has a square gnomon, and that is interesting and can be used to produce a spiral growth pattern. Starting, if you started with a golden rectangle, I'll start off small because I want to build a spiral. You say start, and then you add a square to it. That's not quite a square, but if you add a square to it to make a golden rectangle face in the other direction, then you can add another square to it off 90 degrees, and then you can just keep doing this. Add one there, then add one here, then add one over here. Every time you add it, a square, each of these are supposed to be squares. This one should have come down a little bit more. It's not good if I don't make it more realistic. Okay. Yeah, you always end up with a golden rectangle. It's just that it kind of is a spiraling out golden rectangle. Now, this one in the middle, I started with a golden rectangle, but this spiral actually works in the other way. I could take that one and continue to cut it into cutting a square off it, leaving a golden rectangle. And the spiral, you can draw a spiral working its way out. And I'm just drawing the spiral through these particular points. But this spiral also can go all the way down. It keeps going because you could keep cutting up each of those little golden rectangles into a square and a smaller golden rectangle. And this spiral keeps going down infinitely. And one thing about this spiral is that, good boy, Frosty, it's what they call a self-similar figure, because if you zoom in on it, it looks the exact same, basically, as if you're zoomed out on it. It's always got that same, it's similar is the word, that self-similar. It's like two triangles, like similar triangles, one's bigger, one's smaller. This one's a little bit different because it's actually an infinite curve. So the idea of it being self-similar is more complex than just a big triangle and a small triangle. And this is called a golden spiral. The golden spiral increases at a certain rate. Basically, it increases at a rate since you're adding a square, every time you go through 90 degrees of turning of the spiral, you add a square, and that square is related to it's in the same ratio as the long side of the golden rectangle you started off with. So as it turns out, the radius of the spiral that's constructed this way increases like a factor of 5 or 1.6 for every 90 degrees. So, for example, if you took this spot right here, and then you went through 90 degrees, 180 degrees, 270 degrees, 360 degrees, and then you compared the distance from here to here, basically this distance to this distance, that distance is going to be phi to the 4th power times the distance here. So if I just call that r, this would be phi to the 4th times r, because it gets bigger. Now I'm not going to prove that or anything. It's true from all this geometry. This spiral is just kind of arbitrarily drawn through this particular point. It could go through the center points or like that, but it just grows at a certain rate. Now, phi to the 4th is about a factor of 6, because 1.6 times 1.6 times 1.6 times 1.6, it's approximately 6. It's a little bit more than 6. Anyway, this is called a golden spiral, and it increases at a certain rate. You can see certain spirals in nature. This spiral is also related a little bit to another spiral called a Fibonacci spiral. Fibonacci spiral is constructed like this. You start with little squares, and the side of each square is a Fibonacci number. So I'm going to start with a 1 and a 1. Then I'm going to make a square that's 2, and I'm going to stick it on the other side. And then I'm going to make a square that's 3. Then I'm going to make a square that's 5. So what's happening is I'm sticking on a Fibonacci square onto a Fibonacci rectangle. That is a rectangle formed by the ratio of 2 Fibonacci numbers. And that gives me a resulting rectangle, which is also the ratio of 2 Fibonacci numbers. So this particular rectangle I have here, it's 5 on this side and it's 8 on that side. That's the ratio of 2 Fibonacci numbers. And if I add another square, which is the size of 8, I end up with a rectangle that's 8 on this side and 13 on that side. And since the ratio of 2 Fibonacci numbers is very close to the golden ratio, after you start adding a few of these, this starts to approach a golden rectangle, and it has a square nomen. So when you add on the next Fibonacci number as a square, you get another golden rectangle. They get closer and closer. And you can make a little spiral through here. Let me make it a different color. Green. Let me make it green. You can make a spiral that kind of goes through here in the same way. This is called a Fibonacci spiral. And the thing about the Fibonacci spiral, it doesn't keep going because the Fibonacci numbers just kind of stop. And the other thing is these are only approximately equal to the golden rectangle, not exactly. So this is just similar. It looks a lot like the golden spiral, but it's not really exactly the same shape as a golden spiral. But it has a lot of the same characteristics. And once it gets big enough, because each of these looks really a lot like a golden rectangle, and once it's big enough, it really does look almost exactly like the golden spiral. So this is like an approximation to the golden spiral that gets closer and closer to the golden spiral. So when you talk about spiral growth and the golden ratio, then the Fibonacci numbers are related to that in a certain way. Now, one thing that's an example that's commonly used for spiral growth is the shell of a mollusk. It would be like a snail's shell. Here's a shell from a conch. This shell actually came from Maureen's mother, Betty, who had saved it. Now Maureen has inherited it as a fairly heirloom. Now, there used to be an animal that lived inside here. He would carry this shell on his back. And he'd be like a lot like a snail. A snail is a mollusk, only this one is a sea mollusk. And as he got bigger, he would just need a more room in the shell, so he would secrete this thing that would make the shell bigger. The shell would just start rotating like this, and this end would get bigger, and then eventually he would die, and that's where you get the shell. And the rate of growth of that mollusk has a lot to do with the rate of growth of this spiral. And you can tell that this spiral, it does start getting, the radius increases at a larger rates. So it looks a lot like a spiral like this. And you might say, is there Fibonacci numbers, or is there a golden ratio in this spiral? Well, one way to really test for that is to check for the spiral, and to start at a certain point on the spiral, and then go around 360 degrees. Like here, if I started here, I could go like this, around to there. Now, the radius increases by a certain amount. In this case, it increases by about a factor of 2. For this really to be a golden spiral, or a Fibonacci spiral, that would have to increase by about a factor of 6, which it doesn't. If we go around again one more time, it goes out to here. It goes around by about another factor of 2. This one has a growth factor of about 2, not 6. This is not a golden spiral. It's not a Fibonacci spiral. It just happens to be a spiral. So it's not really Fibonacci here. The answer on this one is Fibonacci here. The answer is no, he isn't. But it is a spiral. Spiral is a form of growth in nature that you see quite a bit. And this particular one, it's really not a Fibonacci one. Okay.